the average value of a continuous function over a closed interval AB is given by the mean value theorem. So this can be visualized if we multiply through by b minus a. So at some x value c, we have f of c, and then multiplying f of c by the length of the interval gives this area over here. And that's equal to the area under the curve, given by the definite integral. So that will be this area over here. And given that these areas are equal, and if we divide through by the length of the interval, we get the average value of the function over that interval. Let's find the average value of this function in this closed interval and identify the x value where this occurs. Well, by the mean value theorem, f of c is equal to 1 over 5 minus 2 by the area under the curve f of x from 2 to 5. So that's basically the integral of x squared with respect to x, and what we get is 1/3 by x cubed on 3 evaluated from 2 to 5. And if you evaluate this, you'll get f of c is equal to 13. And if we equate this to c squared, then this average value occurs at x equals c equals positive root 13, which is inside this interval. If we consider a particle undergoing rectilinear motion over some time interval, and these graphs describe its motion, we'll recall the acceleration is the instantaneous rate of change of velocity with respect to time. So if we separate the variables and integrate both sides, and noting that a is constant in this case, which means that the change in velocity is equal to the area under the acceleration time curve. And in a similar way, the velocity is equal to the instantaneous rate of change of position with respect to time, so we can separate the variables and integrate both sides. And here we can also evaluate this integral on the right using geometry. So that's the area under the velocity time curve. So on the left hand side we have the displacement, and if you substitute for v minus v naught, we can write the displacement in terms of the acceleration also. And the distance can be obtained by integrating the speed with respect to time. So remember that the speed is the magnitude of the instantaneous velocity, and that gives us the distance, which is a scalar quantity, whereas the displacement is a vector quantity which has a direction. A particle travels at a velocity given by the following function, and we're asked to find a displacement from 1 to 4 seconds. Well, the velocity is a rate of change of position with respect to time, and if we substitute for the velocity and separate the variables, we obtain the following expression, which we can integrate on both sides. So from time t equals 1 to 4 seconds, we obtain a position at 1 and 4 seconds. And this here is basically the displacement between 1 to 4 seconds, which is equal to t squared minus 3t evaluated from 1 to 4 seconds. So if you evaluate this, you're going to get 6 meters. A particle travels at the following velocity, and we're asked for the total distance travelled between 1 and 4 seconds. Well, speed is the absolute value of the velocity, and the distance is the area under the speed versus time curve. So in this case, we're going from 1 to 4 seconds. So if this is the velocity curve with a y-intercept of minus 3 and a slope of 2 according to this equation, then the speed is the absolute value of the velocity, so it's going to look something like this. So therefore the total distance travelled is the integral from 1 second to 1.5 seconds, where the speed and velocity are both 0, and the equation of this curve is minus 2t plus 3. And then we add the area under the speed versus time curve from 1.5 seconds to 4 seconds. So the equation for the speed here is 2t minus 3. So basically we're evaluating the area under the speed versus time curve from 1 to 4 seconds piecewise. And post your answer in the comments. A particle travels at the following velocity, and we're asked to show that the area under the acceleration time curve gives the change in velocity between 1 and 4 seconds. So the acceleration is a derivative of the velocity, so that would be 2 meters per second per second. So the acceleration is constant. So from 1 to 4 seconds, the area under the curve is 2 meters per second squared multiplied by 3 seconds, or 4 minus 1. So that gives 6 meters per second. And now if you evaluate the velocity at 4 seconds and subtract the velocity evaluated at 1 second, you should get the exact same result. Recall that a function defined as an integral gives the accumulation of a rate of change. So for example, if we integrate from some value a to some value x, x is a variable and therefore we have an accumulation as x moves to the right. In this case, the accumulation function is g of x, so we have an accumulation from 2 to x that keeps increasing. Now if we integrate over a fixed interval, so say from a to b, then the integral of the rate function, or the rate of change of a quantity, gives the net change of that quantity over the interval. So effectively the area under the curve of the rate function gives the net change of that quantity from a to b. And typically the rate function f of x is going to be given in terms of time, so we want to integrate the rate of change of a quantity over a time interval. And in applied contexts, you'd be given a verbal problem, and you'll translate that into an accumulation or a net change. And we'll do that in the coming examples. The volume of oil in a container increases at a rate of v dash t, and write the definite integral that gives the net change of the rate at which the volume increases between 2 and 6 seconds. So the change in the rate between 2 and 6 seconds can be written as follows, and that's thereby equal to the area under the rate of the rate curve. So basically you differentiate this function and then get the area under the curve by integrating from 2 to 6 seconds. And that's our integral. YouTube subscribers increase at a rate s dash of t per month between 2 and 6 months. And we're asked to write a definite integral that represents the total number of subscribers to date if there are 100 subscribers at the start of the second month. Well, the total subscribers at 6 months is equal to the initial number of subscribers at 2 months plus the total subscribers from 2 to 6 months. So to get that, we integrate the rate of change of the subscribers over time. A population grows at the given rate, and determine the total population after 5 years if the population is 100,000 at 2 years. And we can assume the following quantities for the rate constant and the initial population. So we're asked for the total population at 5 years, and we're given the population at 2 years. So we have 100,000, and then we add the population between 2 and 5 years. So that'll be the integral of the rate over time. So we take the constants outside, and we're integrating e to the kt with respect to time. And that gives you the area under the rate curve. And now you can evaluate this integral, substitute the required values, and post your answer in the comments. A particle's position changes at this rate, and determine the net change of the rate of its position between 3 and 7 seconds. Well, the net change in the rate is going to be x dash of 7 seconds minus the first derivative of position with respect to time evaluated at 3 seconds. So you can get this right away from the rate function or the velocity, or alternatively you can differentiate this to get the acceleration and then obtain the area under the acceleration time curve by integrating from 3 to 7 seconds, and that's going to give you the exact same result. So have a go at doing that and post your answer in the comments. We can use definite integrals to find areas of planar regions. So if we consider this region R, and this blue function as f of x, and the other function as g of x, and we break this region up into infinitely thin rectangles which have a width of dx, then the height of each rectangle is f of x minus g of x. And we multiply this by dx, which gives us the area of that rectangle, and then we integrate from x equals a to x equals b. And that gives us the area of the region. Let's find the area of the region bounded by the curves y equals x squared and y equals x to 1/2 over the interval from 0 to 1. And we're asked to use rectangles that are perpendicular to the x-axis. So therefore the thickness of the rectangle is dx, and to obtain the height, the square root curve lies above the parabolic curve. So what we do is subtract x squared from x to 1/2 to get the height of that rectangle. And then summing up the areas of the rectangle from x equals 0 to 1 is effectively what this integral is doing. And that gives us the area of this entire region. And you can easily evaluate this integral. Find the area between the curve described by this function and the x-axis over the interval from 0 to 1. So the curve looks something like this, and it has a y-intercept of 1 and an x-intercept at 1. And what we do is divide this region from the interval 0 to 1 into vertical rectangles of thickness dx, and multiplying by the height of each rectangle gives us the area of one rectangle, and we integrate from 0 to 1, and that gives us the area of the region. So do the integration and post your answer in the comments. We can also use definite integrals to find the area between curves using functions of y. So suppose this curve is y equals f of x, and this is another one with y equals g of x. And we choose rectangles parallel to the horizontal axes, which have an infinitesimal thickness dy. So to integrate with respect to y, we need to write x in terms of y. So what you do is solve for x, and you'll get x in terms of y. So for example, u of y, and here you'd get x is equal to v of y. And therefore the width of this rectangle is v of y minus u of y, and then multiplying by dy gives the area of that infinitesimally thin rectangle. And then integrating from y equals a to b is effectively summing up the areas of those infinitesimally thin rectangles from a to b. And that gives us the area of this region. Let's find the area of the region bounded by the curves y equals x squared and y equals root x over the interval from 0 to 1. And we're asked to use rectangles that are parallel to the x-axis. So these are horizontal rectangles that are going to have an infinitesimal thickness dy. And to obtain the length of that rectangle, we need to write these equations for these curves in terms of y, because we're going to integrate over y. So x is effectively equal to y squared, and for this case, x is equal to y to the 1/2. And the parabolic curve lies to the right of the square root curve, so we use y to the 1/2, and then subtract y squared to obtain the length of that rectangle. And we integrate from y equals 0 to y equals 1. So this basically sums up the areas of those infinitesimally thin rectangles to give the area of the region. And you can easily evaluate this integral and compare your result with the previous video, where we used the vertical rectangles instead. Let's find the area of the region between this curve, which is a square root function, and the line y equals minus x plus 1, which is going to look something like this. So it intercepts the x-axis at 1 and the y-axis at 1. So to avoid evaluating the integral piecewise, I'm going to select horizontal rectangles, which have a thickness of dy, and therefore we should write the equation of the curve and the line in terms of y. So we have x is equal to 1 minus y. And the line is to the right of the square root curve, so what we do is subtract y squared from 1 minus y. And that's going to give us the width of that rectangle. And we integrate from y equals 0 to the y coordinate of the intersection point between the line and the curve, which I'm going to call a. And that's going to give the area. And now to find a, what you can do is equate these two equations together, and then you can find a, perform the integration, and post your answer in the comments. We can also use definite integrals to find the areas of planar regions that are bounded by several curves, and the curves intersect. So in this case, to find the area of both of these regions, we can use a piecewise integral, and if we designate this function f of x and this one as g of x, and the thickness of each rectangle dx, then the area of the first region is f of x minus g of x, which is the height of one rectangle, and then multiplying by dx gives us the area of that rectangle. And then we integrate from x equals a to x equals b, and that gives us the area of that first region. And similarly for that second region, we integrate from b to c, but this time the height of each rectangle is g of x minus f of x, to give us a positive height for that rectangle, which we integrate with respect to x. And that gives us the area of the second region. And sometimes you have to use some algebra to find the coordinates of that intersection point, which we'll do in the coming examples. Let's find the area of the region bounded by the parabolic curve and the square root curve over the interval from 0 to 2. And we're asked to use rectangles perpendicular to the horizontal axes. So these are going to be vertical rectangles with an infinitesimal thickness dx. So from the interval from 0 to 1, the square root curve lies above the parabolic curve. So we subtract x squared from x to the 1/2 to obtain the height of that rectangle, and we integrate from x equals 0 to x equals 1. Now for the interval from 1 to 2, the parabolic curve lies above the square root curve, so we subtract x to the 1/2 from x squared to get the height of that rectangle, and then multiply by the infinitesimal thickness dx, and integrate from 1 to 2 to obtain the area of that second region. And evaluate these integrals and post your answer in the comments. Let's find the area of the region bounded by these two curves over the interval from 0 to 2. So because we're using horizontal rectangles, we're going to integrate with respect to y. And we need to break this up into 3 regions because we have an intersection point and the integrand is going to change between the second and third regions. So have a think about that. So because we're integrating with respect to y, we're going to write the equation for the parabolic curve in terms of y and the equation for the square root curve also in terms of y. Now for this first region, the parabolic curve lies to the right of the square root curve, so we subtract y squared. Now to obtain the area of the second region, we're going to integrate from y equals 1 to the top of that second region, which is given by this equation. And to obtain the width of that rectangle, we have the square root curve lying to the right of the parabolic curve, so we have y squared minus y to the 1/2. And I'll leave it for you to construct the integral for the third region, and then calculate the area and post your answer in the comments. Let's find the area of the region between these two curves. So for the first curve, it looks like a parabola, and for the second curve, if we set x equals 2, y equals 0, and if we set x equals 1, both curves pass through the point 1, 1. So therefore this is an intersection point. And if we set x equals 0, then y equals 2 to the quarter, which is around 1.2. And if you take the derivative, it's going to approach infinity as x approaches 2. So the curve's going to look something like this. And therefore to avoid evaluating this integral piecewise, we're going to take horizontal rectangles. So the thickness of the rectangle is dy, and we thereby need to write the equations for these curves in terms of y. And then to get the length of that rectangle, we can subtract y to the 2/3 from 2 minus y to the 4. And then integrating from y equals 0 to that intersection point, we obtain the area of the region. So evaluate the integral and post your answer in the comments. We can use definite integrals to find the volume of a solid with square and rectangular cross sections. So suppose we have this curve y is equal to f of x. Well, the height of each square in this case is y, and because it's a square section, the width is also the same. So you can visualize these squares as being parallel to the yz plane. And if we assign this square section an infinitesimal thickness, so that would be dx, well, y squared, which is the area of the square section, multiplied by dx gives us the volume of that section. And then if we sum up the volumes of each of those square sections from x equals a to x equals b, which is what this integral does, then we find the volume of the solid formed by these square sections. So the solid looks something like this. Let's find the volume of a solid with square cross sections that are perpendicular to the x-axis. So effectively the square sections are parallel to the yz plane, as you can visualize in 3D and 2D. And the base is bounded by the curve y equals x to 1/2, x equals 4, which is the vertical line, and the horizontal axis. So therefore, the vertical dimension of the square is described by y, and so is the horizontal dimension, because it's a square. So therefore the area of each square cross section along the horizontal axis is y squared, and we assign a thickness to the square, which is dx, and that gives the volume of one of those squares, and we integrate from 0 to 4 to obtain the volume of the entire solid, which looks something like this. Now y squared is x to the half squared, which is simply x, and now you can evaluate this integral quite easily. And post your answer in the comments. Find the volume of a solid with a circular base and square cross sections that are perpendicular to the horizontal axis. So therefore the sections lie in the yz plane. And the diagonal of the square lies in the xy plane, so the diagonal here is described by 2y, where we're going to take y as the positive root of that equation. And if we're using Pythagoras' theorem, we're going to obtain a length of one of these edges, which are all equal because it's a square section. So therefore the length of the diagonal squared is equal to a squared plus a squared. And therefore a is equal to root 2y. And therefore the area of that square is going to be 2y squared. And we give the section a thickness in the horizontal direction. And we integrate from x equals minus 1 to x equals 1 because the radius of the circle is 1. And that gives us the volume of the solid. So now substitute for y, evaluate the integral, and post your answer in the comments. We can also find the volume of a solid with equilateral triangle cross sections using definite integrals. So if this curve is defined by f of x, then the length of this triangle is y. And because it's an equilateral triangle, all of the edges have the same length. And now we can find the area of this triangle using either trigonometry or Pythagoras' theorem. So half the base squared plus the height of the triangle squared is equal to the length of the hypotenuse squared. And then solving this for h, we get the height of the triangle. And then the area of the triangle is simply 1/2 by the base by the height. And then giving the triangle a thickness dx, the volume of one of those equilateral triangle cross sections is the area by the thickness. And then summing up the volumes of each of those triangular sections from x equals a to b gives us the volume of the solid. So in this case the solid looks something like this. We can also find the volume of solids with isosceles right triangle sections. So these cross sections have two edges the same length with a right angle here. So considering this curve as y equals f of x, then the hypotenuse has a length y, and therefore the height of this isosceles right triangle section can be obtained using Pythagoras' theorem. So therefore the height can be written as follows. And therefore the area of the section is half the base by the height. And then assigning a thickness to this section and multiplying the infinitesimal thickness by the area of the section gives the volume of the section, and then we integrate from x equals a to b to obtain the volume of the solid. So the solid looks something like this. We will also find the volumes of solids formed by semicircular cross sections. So if we have a curve defined by y equals f of x, then the diameter of that semicircle is y. And therefore the area of a circle is pi by the diameter squared on 4, or pi by the radius squared. And we multiply by half to get the area of the semicircle. Now assigning the semicircular section an infinitesimal thickness dx, and multiplying the area by this thickness gives us the volume of that section. And integrating from x equals a to b will give us the volume of the solid. So the solid in this case looks something like this. Let's find the volume of a solid with equilateral triangle cross sections that are perpendicular to the horizontal axes. And the base is bounded by the curve y equals x to the 1/2, the vertical line at x equals 4, and the horizontal axes. So the dimension of the triangle is described by y, and each edge has equal length. And the triangle has equal angles of 60 degrees. So therefore to find the area of this triangle, we designate the height of this right angle triangle as h, and tan 60 degrees is √3, which is the opposite on the adjacent edge. And therefore h is equal to √3 on 2y. And now to obtain the area of this triangle, we multiply 1/2 by the base, which is y, by the height, which is √3 on 2y. And then we assign a thickness to this triangle, which is dx, and that gives the volume of one triangle, and we integrate from 0 to 4 to get the volume of the entire solid. And now you can simplify this and substitute x equals 1/2 into here, and you'll be able to evaluate this integral. Let's find the volume of a solid with isosceles right triangle cross sections that are perpendicular to the horizontal axes or parallel to the yz plane. And the base is bounded by the square root curve, the vertical line x equals 4, and the horizontal axes. So these edges are equal, and the hypotenuse is described by y. So therefore, by Pythagoras, we have a squared plus a squared equals y squared, and therefore a is equal to y on √2. And therefore the area of the triangle is 1/2 by the base, by the height, and then we assign a thickness to the triangle, dx, which gives the volume of one triangle, and then we integrate from 0 to 4 to get the volume of the entire solid. And now you can substitute for y and evaluate the integral. And the solid volume looks something like this. Find the volume of a solid with semicircle cross sections perpendicular to the horizontal axes or parallel to the yz plane, and where the base is bounded by the square root curve, the vertical line x equals 4, and the horizontal axes. Well, the diameter of the circle is described by y, and therefore the area of the circle is pi by the radius squared, and times 1/2 because we're looking at a semicircle. And we assign a semicircle a thickness, which is dx, and that gives the volume of one semicircle, and then we integrate from x equals 0 to 4 to get the volume of the entire solid. And you can substitute for y, evaluate the integral, and the volume of the solid looks something like this. Find the volume of a solid with semicircle cross sections that are perpendicular to the y-axis, and where the base is bounded by the square root curve, the vertical line x equals 4, and the horizontal axes. So the sections are going to be parallel to the xz plane as shown. And the square root curve can be described by x is equal to y squared, meaning that the diameter of the semicircle is going to be 4 minus y squared. And therefore pi by the radius squared, or the diameter squared on 4, gives the area of the circle, and multiplying by 1/2 gives the area of the semicircle. And then assigning a thickness to that semicircle, which is going to be dy, gives the volume of the semicircle section, and then we integrate from y equals 0 to y equals 2, according to this equation. And that gives the volume of the solid, which is going to look something like this. Let's find the volume of a solid with equilateral triangle cross sections that are perpendicular to the y-axis, so therefore they're parallel to the xz plane. And the base is bounded by the parabolic curve, the vertical line x equals 3, and the horizontal axes. So therefore, the edge of that equilateral triangle is 3 minus y to the 1/2 according to that equation. And for the equilateral triangle, every edge has the same length, and every angle is 60 degrees. So tan 60 degrees is root 3, and that's equal to the opposite edge, which is h, on the adjacent. And therefore the height can be written as root 3 on 2 by 3 minus y to the 1/2, and then multiplying this height by the base, which is 3 minus y to the 1/2, and then multiplying this by 1/2 gives the area of that triangle. And we assign a thickness in the y direction, so that's dy, which gives the volume of the section, and then we integrate from y equals 0 to y equals 3 squared according to this equation, and that gives us the volume of the solid. Find the volume of a solid made up of a base that is a semicircle, and semicircle cross sections perpendicular to the horizontal axes. So these cross sections are all parallel to the yz plane. And the diameter of each semicircle is described by this equation, and therefore the area of a circle is pi by the radius squared, and multiplied by 1/2 gives the area of the semicircle. And we assign a thickness dx in the horizontal direction to get the volume of one of those sections, and then integrate from x equals -1 to 1 to get the volume of the solid. And now you can substitute for y, evaluate that integral, and post your answer in the comments. We can use the disk method to find the volume of solids of revolution, and these solids are formed by spinning a two-dimensional section, in this case a triangle, about an axis. So in general, if we have some curve defined by y equals f of x, then the radius of this disk is y, and therefore the area of the disk is pi by the radius squared. And then multiplying by the infinitesimal thickness of the disk gives the volume of this disk, and then we integrate from x equals a to x equals b to get the volume of the revolved solid. And you can imagine that this is going to be a cone. Now we can also revolve a two-dimensional region about the y-axis. So in this case, the disk is going to have a radius of x, and this time the thickness of the disk would be dy. And then we integrate from y equals a to y equals b, and that gives us the volume of the solid. So you just solve for x to basically write x in terms of y, and you'll be able to evaluate that integral. Let's show the following equation describes the volume of a cone using the disk method. Well, given the cone has some radius and some height, and the radius somewhere along the height is defined as r, which is at some distance x from the apex. Then by similar triangles, we can write r on h is equal to r on x, and therefore r can be written as r on h multiplied by x, and that's the radius of any disk along the height. So multiplying pi by the radius squared, so that'll be r squared on h squared multiplied by x squared, gives the area of this disk, which can be visualized in the yz plane, and assigning a thickness dx to this disk gives the volume of the disk, and then we integrate from x equals 0 to x equals h, while taking the constants outside the integral. And this gives the volume of the cone, which you can show evaluates to this result. Find the volume of the solid formed by revolving a region bounded by the parabola y equals 2 and the y-axis, so this region in 2 dimensions being revolved around the y-axis. So therefore the radius of any one of those disks is x, and then pi by x squared gives the area of the disk, and then we assign a disk a thickness in the y direction, which is dy, and that gives the volume of the disk, and then we integrate from y equals 0 to y equals 2 and that gives the volume of the solid. So now you can substitute for x squared from this equation, and you'll be able to find the volume of that solid. Let's find the volume of the resulting solid when a region bounded by the sine curve and the horizontal axis is revolved around the horizontal axis. Well, because the region touches the axis of revolution, we can use disks, and these disks have a radius of sine x, so the area is pi by the radius squared. And then given that disk a thickness in the horizontal direction, gives the volume of that disk, and then we integrate from x equals 0 to x equals pi where the sine curve crosses the horizontal axis. And that gives the volume of the solid. So evaluate the integral and post your answer in the comments. Let's show that the volume of the sphere is given by this equation. Well, a sphere is obtained by revolving this semicircle about the horizontal axis. And using the disk method, the radius of each of those disks is pi by y squared, and given the disk a thickness in the horizontal direction, we get the volume of the disk. And we integrate from x equals minus the radius to the radius. And using the equation of a circle, we know that x squared plus y squared is equal to r squared. Well, you can substitute for y squared, and evaluating that integral gives the volume of the sphere, which is this result. Now we can use the disk method to find the volume of a revolved solid that's obtained by spinning or revolving a two-dimensional section about an arbitrary horizontal or vertical axis. So in this case, the distance to the axes will denote d, and we'll denote the distance from the horizontal axis to the curve as y, where y is equal to f of x, which describes an arbitrary curve. So therefore, the radius of this disk is d plus y, and squaring that and multiplying by pi gives the area of the disk. And then assigning the disk a thickness dx will give the volume of the disk, and then we integrate from x equals a to b to give the volume of the solid. But as we can see, the middle cylinder is hollow, so we need to subtract this volume from the volume of the solid, and that gives the volume of the revolved solid. So you'll see that using the disk method is not always ideal, and we'll learn other methods as we go along. Let's find the volume of the solid formed by revolving this region around the horizontal axis passing through y equals minus 1. And to do that, we're going to use the disk method. Well, the radius of the disk is 1 plus y, and then squaring that and multiplying by pi gives the area of the disk. And assigning a disk an infinitesimal thickness in the horizontal direction gives the volume of the disk. And then we integrate from x equals 0 to x equals 1, which gives the volume of the entire solid. But we have a hollow section in the middle, so what we're going to do is simply subtract the volume of that cylinder in the middle. So that will be pi by the radius of the cylinder squared, and then multiply by the height of the cylinder, which is 1. And now you can substitute for y from this equation, evaluate the integral, and find the volume of the solid. The Washoe method is an effective way to find the volume of a revolved solid if we're spinning a two-dimensional section around an axis where the section does not touch that axis along its length. So we'll give the outer circle of the washer some radius, which is going to be defined by the function of this upper curve. So therefore the outer circle of the washer has the following area. And the radius of the inner circle of the washer is going to be described by this curve. So therefore we subtract the area of that hollow circle. And then giving the washer a thickness in the horizontal direction, we obtain the volume of the washer, and then we integrate from x equals a to b to get the volume of the solid. And I encourage you to try this method on this case, where the region is revolved around the y-axis instead. Let's find the volume of the solid found by revolving the region bounded by the parabola y equals 1 and the y-axis, so this 2D region around the horizontal axis. So in this case the curve does not touch the axes, so we can use washers. So the area of the outer washer, which can be visualized in the YZ plane, is pi by the radius squared, and then minus the area of the inner washer, which is pi multiplied by y squared, and we assign the washer a thickness in the x direction of dx, which gives the volume of that washer, and then we integrate from x equals 0 to x equals 1 according to this equation, and that gives the volume of the solid. And now you can substitute for y and evaluate the integral and post your answer in the comments. Let's find the volume of the solid formed by revolving a region bounded by the parabola x equals 1 and the x-axis. So this 2D region revolved around the y-axis. And because that curve is not touching the axis of revolution, we can use washers. So the outer washer has a radius of 1, so the area is pi by 1 squared, and then minus the area of the inner washer, which has a radius of x, and we assign the washer a thickness in the y direction of dy, which gives the volume of the washer, and then we integrate from y equals 0 to y equals 1, according to this equation. And that gives the volume of the solid, so substitute for x squared, evaluate this integral and post your answer in the comments. Find the volume of the resulting solid when this region is revolved around the y-axis, and we're asked to use washers and the volume of a known solid. So the area of this washer is pi by the outer radius squared, so that will be this x value over here, which is y plus 2. Then minus the area of the inner washer, which is this x value over here, so that will be y squared, all squared. And then we give the washer a thickness in the vertical direction, and then we integrate from y equals 0 to this y value over here. So we can see that these curves intersect at x equals 4, so when x equals 4, y equals 2. And that gives the volume of the upper solid, and we need to add the volume of the lower cone to get the volume of the entire solid. So the cone has a volume of 1/3 by pi, by the radius of the cone squared, and then multiply by the height of the cone. And you could have obtained these values from the y-intercept and the x-intercept of this linear equation. And now you can evaluate the integral and post your answer in the comments. We can also use washers to find the volume of revolved solids formed by sections that are spun around arbitrary horizontal and vertical axes. And let's focus on this second case. So if we designate the distance from this vertical axis to the y-axis as d, and the distance from the y-axis to the outer washer as x1, well, the radius of the outer circle of the washer is then d plus x1. Then squaring that and multiplying by pi gives the area of that outer circle of the washer, and then we subtract the area of the inner circle. So the radius of that inner circle is going to be d plus this distance over here, which we'll designate as x2. And then squaring that and multiplying by pi gives that area of the inner circle. And then given the washer a thickness in the vertical direction, gives the volume of that washer, and then we can integrate from y equals a to y equals b, and that gives the volume of the solid. Now try applying the method to this case over here. Let's find the volume of the solid formed by revolving this region around a horizontal axis passing through y equals -1. So because the region is not touching that axis, we can use washers, and the area of the outer washer is pi by the radius squared, which is 1 plus y squared. And then minus the area of this inner washer, which is pi multiplied by the radius squared. And then we assign a washer a thickness in the horizontal direction, which gives the volume of the washer. And then integrating this from x equals 0 to x equals 1 gives us the volume of the revolved solid. So you can substitute for y equals x from this equation and evaluate the integral. Let's find the volume of the solid formed by revolving this region around a vertical axis passing through x equals -1. So because the region is not touching that axis, it's convenient to use the washer method. So the area of the outer washer is pi by the radius squared, so that would be 1 plus 1, and then minus the area of the inner washer, which is pi by 1 plus x squared. And then assigning the washer a thickness in the vertical direction gives the volume of the washer, and then we can integrate from y equals 0 to y equals 1, and that gives the volume of the solid. And now you can substitute for x from this equation and evaluate the integral and post your answer in the comments. Find the volume of the resulting solid when the region bounded by the parabola and the cubic from x equals 0 to x equals 1. So this region here is revolved around the horizontal line passing through y equals -3. So we can conveniently use washers here because these curves are not touching the axis of revolution. So the area of the outer washer is pi by the radius squared, So the radius is 3 plus y, which is x squared, all squared. And then minus the area of the inner washer would be pi by the radius, so that would be 3 plus y, which is x cubed. And then we give the washer a thickness in the horizontal direction, so that gives the volume of the washer. And then we integrate from x equals 0 to x equals 1, and that gives us the volume of the solid. We can find the length of a planar curve in a closed interval from a to b using the arc length definite integral. So if we construct a triangle that has a length delta s along the curve, well, we can denote the other dimensions as delta x and delta y. And now using Pythagoras' theorem, we obtain the following relationship, and then factoring out delta x squared, and then taking the square root of both sides, and in the limit as delta x goes to 0, we obtain the following expression, where y dash is the derivative of y with respect to x. And if we integrate both sides from a to b, so we have SA and SB, and on the right hand side we integrate from XA to XB. And this here gives us the length of the curve between A and B, or the total distance that a particle travels along the curve. Now you can instead divide through by delta y squared and do similar algebra, and you'll be able to obtain this integral with respect to y. And I'll leave that for you to do as an exercise. Let's verify that the arc length of a line from x equals 0 to x equals 1 is root 2 using both the integral and Pythagoras' theorem. So this is the arc length integral, and we're integrating with respect to x according to this question. Now the derivative is equal to 1, so what we get is an integral from x equals 0 to x equals 1 by the square root of 1 plus 1 squared, which is 2. And now evaluating this integral, you're going to get root 2. And using Pythagoras' theorem, you'll also see the distance between this point and this point along the line is also root 2. Let's find the arc length of the following curve from x equals 1 to x equals 4. So we're integrating over x, so we use the following arc length integral. Now the derivative y dash is equal to x to the 1/2. So therefore the arc length is equal to the integral from x equals 1 to x equals 4, and we're integrating the square root of 1 plus x to the half squared, which is 1 plus x with respect to x. And now you can easily evaluate this integral and post your answer in the comments. Let's find the arc length of the arcsine of x from y equals 0 to y equals pi on 2. And we'll only set up the integral and not evaluate it. So because we're integrating over y, we use the following arc length integral. So to obtain dx dy, we can take the sine of both sides, and therefore dx dy is equal to the cosine of y. So therefore the arc length is equal to the integral from y equals 0 to pi on 2, and we're integrating the square root of 1 plus cosine squared y with respect to y. We can also find the volume of revolved solids using the cylindrical shell method. So if we look at this second case, where we're revolving this two-dimensional region around this vertical axis that's at some distance d from the y-axis. Well, using these hollow cylindrical shells, the surface area of the shell is 2 pi by the radius and height of the shell. So we designate this distance over here as x, and this curve is defined by the function f of x. So therefore 2 pi by the radius and multiply by the height of the shell, which is y, gives us the surface area of that cylinder. And if we give this cylindrical shell an infinitesimal thickness in the horizontal direction, then this expression gives us the volume of this infinitely thin cylindrical shell. And now we can integrate from x equals a to x equals b to get the volume of the revolved solid. And I encourage you to apply this method to this problem over here, where we're revolving this two-dimensional region around the x-axis. Let's find the volume of a solid by revolving a region bounded by the parabola x equals 1 and the horizontal axis, which is this 2D region over here, revolved around the x-axis. And we're going to use cylindrical shells. So this cylindrical shell is hollow, and it has a radius of y, and we multiply 2 pi by the radius, and multiply by the length of the cylinder, which is 1 minus x, and assigning the cylindrical shell a thickness in the vertical direction, gives the volume of this hollow cylinder, and then we integrate from y equals 0 to this point over here, which is y equals 1. and that gives the volume of the entire solid formed by revolving that region. And now we can substitute for x, so that will be y to the 1/2, and you can evaluate this integral and post your answer in the comments. Let's find the volume of the solid formed by revolving a region bounded by the parabola y equals 2 and the y-axis around the y-axis. And what we're going to do is use cylindrical shells, which are hollow as you can see in the xz plane. So every cylindrical shell has a radius of x, and then 2 pi by the radius by the length of that cylinder, which is 2 minus y, gives the area of the hollow cylinder, and then assigning the cylinder a thickness in the horizontal direction of dx, and then integrating from x equals 0 to x equals the square root of 2 according to this equation. And that gives the volume of the solid. And now you can substitute for y is equal to x squared, evaluate that integral, and post your answer in the comments. Let's find the volume of the solid formed by revolving this region around the horizontal axis passing through y is equal to -1. And what we're going to do is use cylindrical shells, which are hollow as we can see in the yz plane. So if we multiply 2 pi by the radius of that cylinder, so that's going to be 1 plus y, and then multiplying by the length of the cylinder is 1 minus x, gives the area of the cylinder. And then we assign a thickness to the cylinder in the vertical direction, and that gives the volume of this thin cylinder, and we evaluate the integral from y equals 0 to y equals 1, and that gives the volume of the solid. So if you substitute for x from this equation, you can evaluate the integral and post your answer in the comments. Let's find the volume of the solid formed by revolving this region around the vertical axis passing through x equals -1. And to do that, we're going to use cylindrical shells. So the area of this shell is 2 pi by the radius, which is 1 plus x, and then multiply by the height of the shell, which is y. And then assigning the shell a thickness in the horizontal direction gives the volume of the shell, and then we integrate from x equals 0 to x equals 1, which gives the volume of the solid. And now you can substitute for y, evaluate the integral, and post your answer in the comments. Let's find the volume of the resulting solid when this region over here is revolved around the y-axis. And we're asked to use cylindrical shells. So the area of this hollow cylindrical shell is 2 pi multiplied by the radius, which is x, and then multiplied by the height of the cylinder. So that would be y is equal to x to the 1/2, and then minus this y value over here, which is x minus 2. So minus x minus 2 is minus x plus 2. And we give the shell a thickness in the horizontal direction, so it'll be dx, and then we integrate from x equals 0 to this intersection point over here. So we can see that the line and curve intersect at x equals 4. And evaluating this integral gives you the volume of the revolved solid.